October 12th, 1838. Kew Bridge, West London. The first beam engine drops into rhythm. Massive cast iron, 30 feet tall, rocking like a ship in slow motion. Steam hisses, valves clack. The great beam rises, falls, rises again. 17 strokes per minute. Each stroke pulls water from the Thames, pushes it toward London homes that have never known reliable supply. The engineer watches. He knows this machine will outlive him. He doesn't know 7 more engines will join it over the next 72 years. Doesn't know every single one will still work nearly 2 centuries later. Doesn't know he's beginning something rare, engineering evolution that never abandons the core principle of maintainability. Welcome to Kew Bridge Steam Museum, where 7 working engines tell a story most modern engineering has forgotten. Stand in the engine hall today. 7 giants surround you. The oldest dates from 1838, the newest from 1910. 72 years of technological evolution, each engine more efficient than the last, each improvement dramatic. Yet walk around the room and you see something impossible by modern standards. Every single one still works, not preserved in glass, not restored to static display. Works. Steam demonstration days fill this hall with the sound of 7 different generations of engineering doing exactly what they were built to do: move water through London. The Metropolitan Water Board built this system. Responsible for supplying one of the world's largest cities, they couldn't afford machines that broke down, wore out, or became obsolete. They needed engineering that could evolve without throwing away what already functioned. Look at the 1838 beam engine first. Early technology, relatively inefficient, but the designers understood something fundamental. They built it in modules. The cylinder separates completely from the frame. 4 massive bolts, accessible from every angle. One person with basic tools can unbolt that cylinder, crane it out, inspect it fully. The bearing blocks? Same principle, removable, replaceable, designed so every critical component could be serviced without dismantling the entire machine. The frame stays standing, the flywheel remains in place. One cylinder fails, you rebuild it, while the building's other engines keep London's water flowing. Modular design sounds obvious now. In 1838, it was revolutionary thinking. 20 years pass. 1858 brings the great stink. When Thames pollution becomes so severe, Parliament considers relocating. London desperately needs more water capacity. The solution arrives in the form of James Watt's rotative beam engine, vastly more powerful than the 1838 design. But here's what matters. The engineers don't abandon their modular philosophy. They improve it. The James Simpson engine introduces compound expansion, using steam twice instead of once, nearly doubling efficiency. Revolutionary advancement. Yet every component remains as accessible as the earlier generation. The high-pressure cylinder separates from the low-pressure cylinder. The valve gear mounts on removable plates. Even the connecting rod bearings use split housings you can service without lifting the rod itself. Technology leaps forward. Maintainability stays constant. Walk around this engine during demonstration days. Steam roars through the system. The massive beam sweeps overhead, yet you can see every working part. No sealed units, no proprietary components, no engineered obsolescence, just iron, brass, steel, and bearings you can inspect visually, measure precisely, repair locally. The mechanics who maintained these engines didn't need specialized diagnostic equipment. They needed good eyes, measuring tools, and understanding of mechanical principles that hadn't changed since Archimedes. If something wore, you could see it wearing. If something misaligned, you could hear it in the engine's rhythm. Visible engineering, audible engineering, trustworthy engineering. By 1869, triple expansion technology arrives. The Grand Junction 90-inch engine represents the cutting edge. Steam passes through 3 cylinders in sequence, extracting energy at each stage, achieving efficiency the 1838 engineers couldn't imagine. Same story, different chapter. This monster engine, capable of pumping millions of gallons daily, maintains every accessibility feature of its predecessors. The cylinders stack vertically, each one removable independently. You can pull the top cylinder for inspection without touching the middle, remove the middle without disturbing the bottom. Service the valve gear on one stage while the other 2 keep running. The bearings tell the whole story. Massive bronze bearings supporting tons of rotating metal, subjected to incredible forces, yet designed for in-place inspection. Split housings open like clamshells, slide out the bearing caps, measure wear with calipers, machine new brass to specification in any workshop with a lathe. No calling manufacturers, no waiting for parts. No discovering the company went bankrupt and replacement components don't exist anymore. The triple expansion engine could run for decades because every wearing part could be remade by competent machinists using drawings, measurements, and standard materials available anywhere iron was worked. That's not just good design, that's engineering philosophy. Consider what the Metropolitan Water Board achieved: 7 distinct generations of technology, each improvement substantial, yet every machine remained serviceable by the same workforce, using the same fundamental skills and tools. When the 1910 engines arrived, representing the absolute pinnacle of reciprocating steam pump technology, the maintenance crews didn't need retraining, principles remained consistent. Bolt patterns changed, cylinder sizes increased, efficiency improved dramatically, but the core philosophy held steady. You can maintain this machine. Watch demonstration days carefully. Steam hisses into cylinders over a century old. Massive beams rock overhead. Flywheels spin with momentum that would crush anyone careless. Yet operation remains transparent. Every valve position visible, every bearing accessible, every safety mechanism mechanical, not electronic, impossible to fail invisibly. The engine overspeeds. A mechanical governor physically blocks the steam valve. Not a sensor sending a signal to a computer that decides whether to respond. Direct mechanical linkage. The governor spins faster. Centrifugal force moves weights outward. Weights close the valve. Physics, not programming. You can see it work. You can trust it. Modern engineers visiting Kew Bridge often experience revelation. These machines violate every contemporary principle of efficiency. Massive installations where compact designs exist, simple mechanisms where complex computer controls could optimize performance, open components where sealed systems would prevent contamination. Yet these engines work, still work. After 186 years, after 152 years, after 114 years, they work. The revelation isn't that old engineering was better. Triple expansion steam pumps represent obsolete technology, surpassed by electric pumps decades ago in efficiency, size, and cost. The revelation is what was lost, somewhere in the drive for optimization, for efficiency, for reducing maintenance labor. Engineering abandoned accessibility. Modern machines ship as sealed units. Specialized diagnostic tools cost more than the equipment they diagnose. Proprietary components mean manufacturers control repairability. Software updates brick functioning hardware. Obsolescence becomes planned, not eventual. The Metropolitan Water Board couldn't afford that philosophy. London's water supply couldn't stop because a manufacturer discontinued a part, or a software company went bankrupt, or a supplier changed ownership. So they built machines where every component could be inspected, measured, remade, and replaced by skilled workers using standard tools and materials that would remain available for generations. They built machines that could be understood. The modular cylinder design demonstrates this perfectly. Each cylinder assembly comprises dozens of components, but they separate cleanly at defined interfaces. All unbolt the steam chest, it lifts away, revealing valves. Remove valve covers, the valve mechanisms become fully accessible. Pull the piston, inspect cylinder walls directly. Each generation of engine improved this modularity. The 1838 cylinders required partial frame disassembly for removal. The 1869 cylinders crane out without touching the frame. The 1910 cylinders include alignment pins, ensuring perfect replacement positioning. Engineering evolution, but in service of maintainability. This approach had costs. These engines occupy enormous buildings. The accessible bearing design means larger, heavier castings. The removable cylinders require cranes and lifting points. Modular construction uses more material than integrated designs. The Metropolitan Water Board accepted those costs because the alternative was worse: stranded assets when technology changed, specialized dependencies on manufacturers, and inability to service critical infrastructure independently. They chose engineering they could control. Walk through Kew Bridge one more time. 7 engines, 72 years of evolution. From simple beam engines to sophisticated triple expansion systems. Each generation more powerful, more efficient, more advanced than the last. Yet stand at any machine and the maintenance story stays consistent. You can see the bearings, you can access the cylinders, you can trace every force path through the structure, you can measure wear with hand tools, you can fabricate replacement parts from standard materials. You can trust mechanical safeties you witness operating. The lesson isn't romantic nostalgia for steam power. The lesson is philosophical. Engineering evolution doesn't require abandoning maintainability. Improved efficiency doesn't demand sealed systems. Advanced technology can remain comprehensible, serviceable, controllable by the people who depend on it. The engineers who built these machines understood something modern engineering often forgets. The best machine isn't the most efficient or the most compact or the most optimized. The best machine is the one that keeps working when you need it most. These 7 engines prove that across 72 years of continuous evolution. They're still proving it today every demonstration day, when steam fills cylinders over a century old and massive beams rock overhead in the rhythm that's powered London since 1838. Still working, still maintainable, still teaching, still honest engineering.